Welcome back to day 24, Advent of Code 2022. Nearing the end now. I'm almost free. Let's see if this one's an easier one. Alright. Day 24, Blizzard Basin. With everything replanted for next year, and with elephants and monkeys to tend the grove, you and the elves leave for the extraction point. Partway up the mountain that shields the grove is a flat, open area that serves as the extraction point. It's a bit of a climb, but nothing the expedition can't handle. At least that would normally be true. Now that the mountain is covered in snow, things have become more difficult than the elves are used to. They're not used to the mountain being covered in snow? As the expedition reaches a valley that must be traversed to reach the extraction site, you find that strong, turbulent winds are pushing small blizzards of snow and sharp ice around the valley. It's a good thing everyone packed It's a good thing everyone packed warm clothes. To make it across safely, you'll need to find a way to avoid them. Fortunately, it's easy to see all of this from the entrance to the valley, so you make a map of the valley and the blizzards. So these are the walls of the valley. Dot is clear ground, otherwise we have blizzards, okay? Due to conservation of blizzard energy, as a blizzard reaches the wall of the valley, a new blizzard forms on the opposite side of the valley, moving in the same direction. Huh? Okay. After another minute, the bottom downward moving blizzard has been replaced with a new downward moving blizzard at the top of the valley instead. I see, okay. So they move forward. Because blizzards are made of tiny snowflakes, they pass right through each other. After another minute, both blizzards temporarily occupy the same position marked 2. After another minute, the situation resolves itself, giving each blizzard back its personal space. Finally, after another minute... Okay. So you begin in the only non-war position in the top row. You need to reach the non-war position in the bottom row. You can move up, down, left, or right, or you can wait in place. You and the blizzards act simultaneously. You cannot share a position with a blizzard. The fastest way to reach your goal requires 18 steps. Okay. Yikes. So sort of like... So a shortest path algorithm like A star or something would actually work. But we have to know exactly what the map will look like. Every step. Yeah, can do that. For a given cell, we're only interested in when it's not occupied with blizzards, right? So okay, whatever. Let's extract the map first. So we want okay. Grid. Is an empty list. Alright, so for each line, grid dot append have a look at what we're dealing with here. If they're the same, if it's a square, not. No, it's clearly not a square. So the ones that are going horizontally repeat every 27 steps. The ones that are going the ones that are going vertically repeat every 27 steps. The ones that are going horizontally repeat every 122. So for every cell, we can work out exactly so it's actually 25 and 120. There's 25 different spots. None of them are going into the entrance or exit. That's useful. So you can, for workout out of, so what's 120? What's the, how do you work out the highest common multiple? It's like 100 and... Maybe you multiply them together and divide by the common factor. So be 600. Okay. 600. So every 600 steps, that whole thing repeats. So we just gotta compute 600 different maps, basically. Either that, or for each cell, we just record which integers, or what's easier? Alright, let's do this properly though. So, we use import fraction from fractions, import greatest common divisor. LCM equals height minus 2 times width minus 2 because we're taking off the walls, divided by GCD of height minus 2, width minus 2. That's how many different maps we need. Should I actually make a visual one? This, whatever, let's just make 600 maps. We can do that. Okay. Grids. Grids equals so be what, 600 times 27 times 122, that's like a couple of million. Yeah, that's fine. I mean, the alternative is to just, I mean, the more sensible memory-wise thing is to just store for every cell a set of integers for which it is... No, I can do this way, actually. This is not that hard either. So, okay, so for every cell, we store the integers, set of integers from 0 to 600, 0 to 5999, 599, at which it will be empty. Let's try that approach, then I don't have to make lots of maps. So we want for each so we want clear weather map, say. It will take a cell location as a tuple, and it will return a set integers from 0 to LCM minus 1. Yeah, let's do this. Okay. So basically my brain's thinking of all sorts of different approaches. Let's stick with this one approach. I mean, this actually seems to work in my head. So, all right. So, for I in range height -2. For j in range, let's say starting from 1, finishing on at -2. For j in range 1 with -1. All right, so we're on a cell. We want to work out which days. Okay, so the all possible days is set range LCM. That's, for now we're just assuming it's has a blizzard every day. No, other way around. Blizzards equals an empty set. We now look at the row and the column it's in, and for every blizzard we see, we work out when that blizzard will cross our cell. And add that time to our weather map. So Instead of typing height -2 all the time, let's should I just get rid of the walls in this grid? It'll make it easier. Let's say grid.append from 1 to -1. And then we'll cut out the top and the bottom. We can manually code the entrances and exits. It's fine. Alright, now we can just deal with height and width. It's just cleaner. Alright, let's just try running this, make sure we've got not hitting anything. Normal fractions import GCD, isn't that a thing? It is a thing, look. Damn it, let's look this up. Python GCD. It's math.gcd? Fine. They must have moved it. I seem to remember it being in fractions. Okay. So we've got a current cell. All right. So let's look at the row for Liz equals, so we want to get grid okay, so if Liz in, so we're looking in the row, so if it's this or this, then we want to work out at what time will this one cross back to it? So should be a straightforward calculation. We'll say if Liz equals, just do them one at a time. So this one's the easier one. So it's currently at it. We are at I, it's at it, and it's going forwards. So it will. So in width, if we go a full width, it will go back to it. So if we do, hang on. So we do width plus okay, this is not complicated. I just width plus I minus it. That's the time it will arrive at. Why am I adding width? That's not necessarily. That I need to draw something here. That seems right, yeah. I minus it sent width. First hit, that's the first time it's going to hit our cell. And then we want to repeat every... I want to keep adding width until... So, for... medium range, so for however many times it fits into the LCM, we do K times width plus first hit. Well, don't need to make so many variables, let's do this. That is a blizzard. So we do blizzards dot add that. Is that right? whatever. Hello, Ku. And if we're going the other way, we do. Today's the final one? No, it's 24 today. Tomorrow is 25. Is it brutal? Not brutal. It's involved, but I can sort of see what to do. It's sort of a, it's kind of like pathfinding, but every step you take, every single one of these little arrows will move in the direction they are moving, and roll around the map as well. Wrap back to the other side of the map. So it's kind of like a moving through a history graph, basically. So I'm just calculating for each cell, I'm calculating which times, because it's all going to repeat every multiple of width and height. So I'm just calculating which times out of, in this case, 600 steps the whole map repeats, which times the cell is going to be empty. And then once I have that information, you can just pathfind like that, where neighbors will just take care of that, check which cells are empty at which times. So I'm just trying to do the arithmetic right now. So it's like for every blizzard, I'm counting, so for each cell on the map, I'm looking at the blizzards in the row and the column and check at which times they will cross my cell. So going the other way, it will be just the other way around. It minus I is width. And we want to do the same for the height. Blizz equals grid. Alright, we don't need so many variables. Let's say, oh, that's fine. Blizz equals grid I JT. So if it's down, wait, what's down? B. Okay. Oh, I also forgot to put in J here. Okay, so, and then here we want I, that'll be K times height plus J minus JT percent height. And then the other one will be the other way around. JT minus J. This one is this symbol. Okay, so at this point we've computed all the a set of all the times. Oh wait, no. It's not a tuple. It is a time. It's a time, so take that out. A time from 0 to 600, 0 to 599 even. Blizzards. Let's refactor. Let's call this Blizz times. So let's check this. If we were sitting on this right now, then we would get I minus IT being 0. So we would get 0 being added to the time. Okay. So now we have a set of all times, but we want to invert it just because we want to know really when it's clear. We don't care. Yeah, okay, so we say clear weather map of ij equals, we want set range of the lowest common multiple minus all the times at which we have blizzards. Let's try running that. IT in range width blizz equals grid itj. Got this the wrong way around. This should be named JT. So we're looking along the row. Then we should have J minus JT. JT minus J. And then what? IT in range. Height. Should get IT J. Everything was the wrong way around. And then it'll be height plus I minus IT. IT minus I. Okay. Looks good. Print for KV in clear weather map to items. Print KV. That looks promising. Let's try printing a length of fee. I want to see how often each cell is empty. It shouldn't be that often because there's a lot of blizzards. And this is out of 600, so it's roughly a third of the time to a half the time that it's empty. Does that make sense? So for example, here, I can believe that. Okay. Alright, it seems plausible. Okay, so now what? We now need to create like we could do BFS here. Or do we want A star? Would BFS be a bit slow? Let's try BFS. Reduces the amount of things we get wrong. Alright, so let's copy BFS from earlier problem. What's it? 15. No, 14, 13. What was the one with the... Alright, let's close all these because it's confusing. Alright, I'll load up the calendar. So I think it was like... "12" was the one where I did pathfinding. Here we go. Let's just copy that. BFS. So BFS given start. So start would be essentially -1, 0, essentially. So we're off the map. So let's check this. BFS. We want to use a Q. Queued up at start. G dist equals start 0. So we don't. So we want start and a timestamp wrapped up as a tuple. So start 0. So actually, just to be clearer, starting node equals both the position and the time. The time only goes to 599 LCM. G dot plot. Put that in the queue. Distance is 0. Okay, close set equals set. We don't need both gdist and close set, do we? They're the same thing, so hang on. So current equals q.get. We do a goal check. We need a get neighbors method. We don't need close set. We just say if it's in gdist. gdist neighbor equals gdist current plus 1. That's correct. Queued up with neighbor. That's all correct. The goal check and the get neighbors need to be checked. Well, the goal check is easy. If current, so the positional element of the node is, so it's going to be height width minus 1. So we're on position height, which is past the end of the map. And width minus 1, yes. Okay, everything, that's all correct. We just need get neighbors now. So we have node. So we have a position and a time equals node unpacked. So first we want to find the positional neighbors. Then we want to work out for each of them whether they can be reached in time. So firstly, we have to override if it's at the if it's outside the map. Okay. If pos equals, so it's -1, 0, neighbors equal positional neighbors is just 0, 0. Else for delta so we've got -1. So let's say go right first, go left first. So right, go down, go left, go up. Neighbor equals pos 0 plus tx pos 1 plus ty if so we want 0, so we want 0 is less than or equal to neighbor 0. So this is the height, it's less than height, and 0 is less than or equal to neighbor 1 is less than width. Neighbors dot append neighbor. But we also want a special case if pos is height -1, width -1. Then we also want to add well, we can do that at the end. Okay, so now we've got the positional neighbors. Result equals the final list of nodes to move to, because node is a neighbor with time. So we handle the wait move. Result dot append pos, and then we want time plus 1% LCM. So we can always wait in place, except we can't always wait in place. So hang on. Okay, hang on. We want to count ourselves as a neighbor too. Because we can wait in place. And just treat that as a place we move to. Okay, so for neighbor in neighbors, the one thing we, the things we need to check is if we're outside the map, then this automatically passes. This automatically counts. New time equals time plus 1% LCM. If we're outside the map, so if neighbor in -1 0 height minus height width -1. Oh, we didn't add. Okay, hang on. If pause equals height width -1, neighbors dot append the goal location. You can always step onto those because there's no blizzards there. Alright, so now we've got the true list of all positional neighbors, including the starting place. Should we say you can't go back to the... Technically you can go back there, but let's not allow you to, because it's equivalent to just waiting. So it's pointless. Also, if we're near the goal, there's no point going to any other neighbors. Let's just force you to go to the goal. So let's say this elif pause equals neighbors equals there's a better way to do this. Let's just immediately return early if we're near the goal. New time equals that. Alright, so if pause equals that, then we just return that with the new time. That's the only neighbor, and we should only go there because that's the goal. Okay. All right. Otherwise, we're actually dealing with positional neighbors. So if we're there, let me go there, or we can either wait in place or we can go there. Otherwise, we add all the positional neighbors. Okay. Alright, for each neighbor. If it's equal to the start node, then that's fine. Oh, also this needs to be a list. Because it's a list of nodes. Okay. So we do neighbor new time, else alright, so otherwise it's just a normal node. This is the point at which we check everything rests on this step here, checking the clear weather map. If new time is in clear weather map neighbor, so the clear weather map maps a physical node, positional node, to a set of times at which it's clear. So if it's in the clear map, I mean, one thing that could go wrong is the clear map not being correct. But we'll have to check that against the test example. If it's in the clear map, man, this is part 1. Then we result dot append neighbor new time. Return results. That's it. Get neighbors. Let me run BFS on a start node. Print BFS on the start location. Anything else? Run it. It's going to take a long time, isn't it? We need I'll just leave it for a while. Let's figure out what we can. Should I run it on the test example? The number of possible nodes is height times width times LCM. It's going to be like a couple of million. But that should be okay. We don't have a measure of progress here. Okay, so I mean, it should terminate, so it's, I don't know, we could be stuck in an infinite loop. So every time we put something in the queue, we also add it to gdist, so we never add it a second time. Okay, let's try it on the test example then. See if it actually makes sense. I mean, because switch to using A star. Okay, it's still stuck in an infinite loop, so that's a good sign. That means it's not just too slow. Make sure it's actually starting the BFS. It is, okay. Okay. What sizes are we dealing with here? 1, 2, 3, 4, 5, 6. 4. 6 and 4, okay. Current equals by printing current, then see what we get. It's stuck on this one. Three, 5, 4. Is the queue empty? No, because so you printed this one. Oh, that's weird. How would this ever happen? So three, 5, 4. So neighbor and get neighbors. I don't know. Print neighbor. What's going on here? So 355 is a neighbor. gdist neighbor equals gdist current plus 1 queued up put neighbor. Also, I don't understand, why would it get stuck at any point? These are just steps. There's no while loop in here, is there? What is it? Okay, where is it currently? What step is it at now? So it's not going through. So it's printed that. Try, I don't know, printing. That. It's just that neighbor. We are getting some neighbors, so that does look like what it should look like. All right. Why does it get stuck here? 355. What is, okay, 355 is that row. That. So we're there. Am I waiting there forever? What's going on? Still, even if you're waiting there forever, we should be printing new neighbors. Maybe I haven't quite given the correct goal here. So if we're there, as we are. Oh, well, that's wrong. That should be height. Still, I wouldn't expect it to... I don't know. Take that. So we should go to the outside the map. Try that again. I don't understand why it was hanging though. 18, there we go. I don't know. Don't care. Can we stop printing stuff now? Alright. Let's go back to the big one. $227? I mean, it should be quick. It's only up to like 1 million, and it's probably finishing early. Fuck. 227. But we got it right in the test example. That makes it annoying. Do we have the right values here? Because that's one thing that's 25, 120, and 600. Yeah, that sounds right. Alright, so if it's in clear weather map, so we need to check that the clear weather map is actually correct, because that's something I'm relying on a lot of calculations for. Now we're using the right symbols. Yeah. Oh crap. There's a mistake. Width, 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 width. Height, 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 height. Alright. Try again. 245. Alright, let's try that. Correct. Part 2. Oh, do I have any food? It's 3 PM and I haven't had lunch yet. Let's try and solve this. Alright, as the expedition reaches the far side of the valley, one of the elves looks especially dismayed. He forgot his snacks at the entrance to the valley. Since you're so good at dodging blizzards, the house... blah 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 blah. How quickly can you make it from the start to the goal, and then back to the start, then back to the goal? In the above example, the first trip to the goal takes 18 minutes, the trip back to the start takes 23 minutes, the trip back to the goal again takes 13 minutes, for a total time of 54 minutes. Alright, it's not... Okay, a couple of things I need to... tweak, but it's not that difficult. We just run BFS 3 times. But there's a couple of things I've hard-coded that I need to un-hard-code now, so the get neighbors map needs to be a bit more generic. So we say So fortunately, it is the case of independently getting to the goal as early as possible, then back to the start as early as possible. Because in the worst case, you could just wait until the next available time. And so it's never the case that you want to, that it's better to, say, arrive later or whatever. Okay, so, all right, let me just tweak this. So if we have, we don't actually want to override this here. We want to add all neighbors. So we want to say, okay, so take that out. All right. If we're there, then the neighbors are the start or here. Okay. Else, our neighbors are ourselves and a bunch of places. Okay. Hang on. Elif Oz is height width -1. Neighbors equals Oz height -1 width -1, because you can come back from the goal. Else, we can stay put. We can do one of the regular neighbors. But we can also say if Oz is 0, 0, neighbors dot append -1, 0. Elif Oz is height -1 width -1. Neighbors dot append height width -1. So that accounts for those places as well. Now, for each of these places, if it's -1, 0 outside the map, that's valid. Elif neighbor is height width -1. So let's just say this. If it's outside the map on the start or goal locations, we append that, it's fine. Otherwise, we do that. And result. Let's check that this still actually... Oh no, we're not done yet. No, that's fine. We just needed to tweak to get neighbors, right? Yeah, 2, 4, 5. Okay, that still works. That's generic. We're allowed to move back and forth from the start and goal locations. They're not considered start or goal, according to get neighbors. They're just places you can go. BFS will determine whether we hit the goal. Alright, so okay. Time equals BFS start. So we're actually gonna have to start at specified time. So we start at time equals 0. Let's say time equals 0. Or better yet, we give it a position and a time and let the BFS wrap it up, because it doesn't make sense for us to do that. So let's say so the time becomes that. Okay. Hang on. Steps equals that. Steps is not the same as time. We add steps to time. Print arrived at goal at time. So we now want to say time plus equals steps. Time. Alright, just make sure this works still. 2, 4, 5. Okay. Now we do the next trip. Second trip. So we want to say we need a goal actually. So we want start, this is how we do it. We start, end, time. Okay. Start, goal, time. Goal, we will use goal here because goal indicates that's where we need to get to, so. If current 0 is goal, return that. Okay. Okay, test that again. Okay, fine. So we now start from end. We want to reach start, and we start from time, the new time, whatever. Okay, now run that, see what happens. End at 528, and now we want to repeat and go back to the goal. Third trip. We go from start to end at Current time. Alright, let's try this. $7.98? Could be off by 1 if I'm not adding these times correctly, so whatever, try it. Did I get that right? We're going 3 first trip back to the start, trip back to the goal. Alright, try that. Correct. Took a while to code, but that was not particularly hard. It's just standard searching, but you need to take history into account, time, what the neighbor function looks like at any given time. Sometimes referred to as history graphs, because you have an efficient way of maintaining the history of the graph. Solved in 30 minutes. Interesting. Yeah, I mean, unpacking the blizzards could take some time. The blizzard information. I mean, I started an hour late here, so 1.5 hours late, so I could have got way better rank. Alright, tomorrow is the final day, and hopefully it'll be a nice easy one, because it usually is. It looks like this is actually building a picture of the journey we're taking. Got the ocean. I guess this is a volcano, a mountain. With lava, magma. That was a nice problem, I like that. Yeah, nothing much to say about that. It's just I could have used A star. Well, I mean that ran really quickly, so there was no point bothering with A star. I assumed I would need to. It just seems like something that might need a heuristic, but no, it's fast. Just use BFS. Even DFS. No, not DFS. BFS. We want to get the shortest path. Okay, well, see you tomorrow for the final day.